Today we're going to learn about topic 3, solution preparation. Our learning goals for today are to explain why chemists prepare solutions, define the standards and stock solution, as well as dilution, explain the procedure to prepare a standard solution, as well as to dilute a solution, and perform calculations involving dilutions using the dilution equation. Many chemical reactions involve aqueous solution. And as we know in chemistry, it's very quantitative. So we need to have a way of being able to define exactly how much solute we have. So in order to give reliable data, it's important that solutions are carefully prepared using known concentrations. And we spent a lot of time learning how to figure out those concentrations. Today, we're going to see how we can actually prepare a solution to use for laboratory experiments. There are two main types of solutions. The first one is known as a standard solution. So that's any solution with a known concentration. Another term for solution is also a stock solution. So a solution that is in stock or on the shelf. And it's typically concentrated. So an example of that would be if you go into any traditional lab. So for example, when I was going through doing my PhD, I had my lab bench, and if you looked at the top of that lab bench, there would be a whole series of solutions that I've made up, and they were all labeled. So those are all stock solutions. They're solutions that are labeled that are on your shelf. And scientists will typically use those as a way to try to cut down on having to make a solution every time, and they'll take a little bit of it every time they need it. So for the first part of this lesson, we're going to learn how to actually prepare a solution from a solid. So to prepare a solution, we typically need precision equipment because we want to make sure that we know exactly how much solute is dissolved and have a specific volume of solution. So to do that, we're going to be using a volumetric flask, okay, which is we can see over here. And there's a whole series of different types of volumetric flasks, and they're these pear-shaped containers that have an elongated neck. Okay, and they're designed to hold a specific volume of solution. So each one can only be used to measure a specific volume. So for example, these large ones here will probably hold a liter. These kind of medium-sized ones will hold 500 milliliters of solution. And some of these smaller ones here might be 250 milliliters, 100 milliliters, and so on. But they're only designed to hold a specific volume. Okay. Now, why would we use a volumetric flask to prepare a solution? Okay. The other equipment that we would have would be a beaker. Now, take a moment and think, why do you think it'll be a lot more accurate in terms of the volume of the solution that we have if we use a volumetric flask versus a beaker? If you notice the diameter of these flasks, you'll notice that the diameter on a beaker is significantly larger than the diameter over here. And what we're going to find is on a volumetric flask, there's going to be a marker that says this is the specific volume. So if you reach up to this point, you have 500 mils of solution. So in here, because the diameter in here is very small, if you're off by a little bit, it doesn't result in a large volume of water. Versus, let's say if you're filling this up to the 500 mil mark here using a beaker and you're a little bit higher, because the diameter of this beaker is very large, that will result in a greater volume of water and a bigger difference in terms of the air for your solution that you prepared. So if we're trying to make a precise solution, we're typically going to be using a volumetric flask. Now, to actually make up a solution, what we're going to do is we're going to actually measure out the amount of solid that we need using a scale. Okay, and what we'll typically do is we'll have our volumetric flask filled a quarter to a third with water. And then from there, we're going to add in our solid. And from there, we're going to shake it, as you can see over here. And that's the nice thing about these flasks is by having it elongated and kind of extended on the top, it allows you to shake it and not having to worry about any chemical leaving the flask. So you can shake it pretty vigorously and make sure that you get everything dissolved. And then from there, we're just going to top it up with water up until we have that mark that's indicated on each flask. And each flask will have a mark at a different point because these are all handmade pieces of equipment that are carefully measured to make sure that they actually can contain that specified volume. Okay, so just to recap, we're going to go through and measure the mass of the solute using a scale. We're going to fill up our volumetric flask with a quarter to a third full of water. We're going to add in our solute. We're going to shake it to dissolve it. And then from there, we're going to continue to add water until we've reached the fill line. And from there, we will have our newly made solution, which of course we need to label with the concentration and what's in there. Now, in terms of dilution, it is the process of decreasing the concentration of a solution, typically by adding more solvent. Okay, and this is the same thing that you do if you have concentrated fruit juice and you add water to it, or you have fabric softener and you're adding water to it, or you have a cleaning product and you're adding water to it. Whenever we're diluting something, we're making the solute in there less concentrated. Okay? And this is a very simple procedure, and it's something that's very commonly done in a lab. So similar to preparing solutions, when we're carrying out a dilution, we're going to use precise volumes. And with that, a graduated cylinder may actually not be precise enough for some of the analytical work that's required. So pipettes are commonly used, and there are two types of pipettes. The first is a volumetric pipette, which delivers a fixed volume of solution, similar to the volumetric flask, which holds a fixed amount. And this would be an example here where it only holds a specified volume. So this one here would only hold 10 mils of water. Okay. Another type is, let's say you need only like say 5.5 milliliters of water, is a graduated pipette, which is just as accurate, but it has a grading system where you can see the actual volumes and you can adjust based on how much you actually need. So diluting a solution is very similar to preparing a standard solution from a solid. Okay, so we're going to go through and we're going to use our volumetric graduated pipette. We're going to take the amount of solute that we need, which is originally dissolved in water and typically from a concentrated solution. We're going to add that to a volumetric flask that is already partially filled with a quarter of water. We'll add in the liquid using our pipette. From there, we're going to shake it and then top up our volume up to the top. Okay, and that basically the same idea, except when we're dealing with our solute, it's already in solution. So we just need to use a pipette, whether it be a volumetric or a graduated, to measure its volume. There's another term that's important and something that you may come across, and that's a serial dilution. So a serial dilution is just a stepwise dilution of a substance. And this isn't something that we're going to be learning how to calculate, but I just want to make sure that you guys have all seen it. Okay, and what it would be is if you go through and you take, if you have a concentrated solution, and then you just carry out a series of dilutions. Okay, so an example would be if you take a concentrated solution, you take 1 milliliter of it and add 9 mils of water. And then you shake it up. And then you take 1 mil of that and you add it to 9 mils of water, and then you shake that. And then you take 1 mil of that and you add it to 9 mils of water, and so on and so forth. And you're progressively reducing the concentration of your substance tenfold each time you go through. And these dilutions will typically be in a stepwise manner using a progressive decrease in concentration. What we're going to spend the rest of our time doing is learning how to actually perform calculations involving dilutions. So how do we know how much of the solute do we actually need? Now, this is actually relatively straightforward, okay? So this is because when we think about it, when we're going from a concentrated to a dilute solution, the amount of solute actually doesn't change. All that we're doing is adding more water to it. So the amount of solute before the dilution is the same as the amount of solute after the dilution. So we can say that the initial number of moles present is equal to the final number of moles present. Now, because of this, we can derive an equation. We know that N is equal to concentration times volume. So we can derive an equation. So we can say, if I plug in N is equal to CV into this N1 is equal to N2, we get C1 V1 is equal to C2 V2, where over here, this is dealing with our initial concentration, and this is our initial volume of solute. This is our final concentration of our solution and our final volume, okay? So if we're looking at this equation, okay, this part here deals with the concentrated solution. And the one here for C2V2 deals with the diluted concentration. Now, as we can see based on this equation, concentration is inversely related to the solution's volume. So if concentration's high here, it's going to be low here, and vice versa. Same thing goes for the volume, because the products of C times V will always have to be equal. Right? So we're going to try to go through a few sample problems to get a little bit comfortable using this equation. So in this question, it says water is added to 0.2 liter of 2.40 m NH3, where if we remember, capital M is a unit, means moles per liter. Okay, so in here, water is added to 0.200 liter of 2.4 mole per liter NH3 cleaning solution until the final volume is 1 liter. And we're asked to find the molar concentration of the final diluted solution. So to do these problems, what I like to do is actually set up a table to simplify it. And what I'll always do is I'll set it up where we have concentrated on the left and diluted on the right. With concentrated, that's your C1 and V1. With your diluted, that's C2 and V2. Okay, so in here, the question says water is added to 0.2 liter of 2.4 molar NH3. That has to be your initial concentrated solution. So we can say V1 is 0.2 liters, and we can say C1 is 2.4 molar. In the question, we're told that the final volume is 1 liter, so we can say V2 is 1.00 liter, and we're asked to solve for the final concentration, so that is C2. So in here, we know C1 V1 is equal to C2 V2. We can rearrange for C2. So we have C1 V1 divided by V2. And then from there, it's just a matter of plugging in. And we'll get a final concentration of 0.480 molar, or 0.48 moles per liter. Now, if we notice, this concentration is lower than the initial concentration we were given, which makes sense because it was diluted, right? And we also notice in terms of the volume, your initial volume is lower, your final volume is higher. We will always see that inverse relationship. Okay. Now, let's try sample problem 2. A student is instructed to dilute some concentrated HCl, and it says that it's 36%, to make 4 liter of 10% solution. What volume of hydrochloric acid solution should the student initially measure to do this? So similar to the last problem, we're going to set up our table, our concentrated and diluted. In the question, we're told we're starting off with some concentrated HCl, and that's 36%, so that's our C1. We're told we're trying to make this solution, so it's 4 liters, that's V2, and our final concentration is 10%. Now, if you're not sure whether it's the initial or final and which numbers go together, we will often see that the numbers that go together are going to be very close together in terms of the information that's given. Okay, and just try to look at the wording. If you're trying to make this solution, that is always going to be the diluted. If you're starting with this, that's going to be your concentrated. Okay. In the question, we're asked for what volume of hydrochloric acid should we initially measure? So that is V1. Okay, so we know C1 V1 is equal to C2 V2. If we rearrange, V1 is equal to C2 V2 over C1. And from there, we're plugging in. So we have 10% times 4 liters divided by 36%. Our percentages cancel out, and we get an answer of 1.1 liter. Okay. One question that could be added as a follow-up was how much water needed to be added to make this solution. Take a moment and think about it. If you thought that it would be your V2 minus your V1, you're absolutely correct. Okay, so to find out the amount of water that was added, we would just take 4 minus 1.1. And we'd get 2.9 liters. Yeah, last problem. What volume of 12 molar HCl must be used to make 2 liter of a 0.1 molar solution? So we're setting up our table. We have our V2 is 2 liters, C2 is 0.1 molar. Our initial concentration is 12 molar, so C1 is 12 M, and we're trying to solve for V1. So we have C1 V1 is equal to C2 V2, rearrange for V1, and then from there we're plugging in our values. And we get 0.016666667 liters, and we'll round that to 0.017 liters. Ooh, actually one more. So if we go through and we look at sample problem 4, it says, what is the concentration of a solution that is made using 45 milliliters of 18 molar H2SO4 diluted to 500 mils? So we have C1 V1, we're given V2, and we're trying to solve for C2. So we can go through, rearrange our equation for C2, C1 V1 over V2, plug in our values, and we're going to get 1.6 molar. So that's all I really wanted to go through for today. We will go through and practice doing these calculations in class, and if you have any questions, please do not hesitate to ask.